Okay, so we're 30 seconds late. Welcome to today's lecture. Um, Last time we talked about, actually, let me switch on the light here so you see me better. Hopefully, there's some, so let me try to get rid of the sun here. I mean, sun is nice. Oh, that doesn't work. Anyway, um, yes, so last time we talked about the camera transformation, since we're moving from the more ray tracing based approaches that we've used so far to those that are necessary for rasterization, which of course is a big part of graphics still today, likely to change over the next couple of years. Ray tracing is getting more and more support with hardware acceleration, and there's a clear will by NVIDIA and others to really make ray tracing the primary goal of doing graphics going forward, but we're still not there yet, and probably will take a couple of years until we get there. But it's clear that rasterization will be around, and it's actually the more efficient methods for certain types of applications. So it is absolutely worth looking into this. So last time we looked at what we need in order to take 3D objects and project them onto a 2D screen. So 3D to 2D perspective projection, but we also included the orthographic projection, which is quite a bit simpler. The other key element, and again, projection is a key element in graphics, and also today's part, clipping, is part of it's needed for rasterization, but that's not why we're discussing it here, but because it is a fundamental operation in graphics applications of various sorts. And so it's important to know about the algorithms available there. But we discussed them in the context of rasterization, like we discussed a lot of the algorithms in the context of ray tracing in the first half of this course here. So let's dive right in. It's essentially starting already what I already started saying here. So if you project primitives, triangles, lines, whatever, onto a 2D screen, they might fall partially inside and partially outside of the window that we will at the end eventually render. And at some point, we need to eliminate the parts of the geometry that are outside of the window, so that are not visible. And we want to do this as early as possible in the pipeline, because otherwise we're spending resources on processing something that at the end will not be visible, which makes no sense. And the clipping operation can happen, usually happens after the projection and the transformation from 3D to 2D, but as we'll see a little bit later, we can actually do some of that also in 3D. The key element is not, there's two reasons why we need to do the clipping operations. The one is that certain devices can simply not draw outside of the window. If you think about a mechanical plotter, right, if you still know these kind of devices that are not as common anymore, but they can't move their pen outside of the machine, and so that they simply cannot deal with geometry that's outside. But also, if the algorithm that you use for drawing could handle geometry that is outside of the window, and just essentially just render the part that's inside. When we talk about rasterization next, we'll see that for rasterization itself, it's not a problem to just restrict itself to just painting the pixels inside the window, even if the triangle is larger than that. However, for efficiency reasons, in hardware, we implement the representation of the geometry in 2D in a compact form, and we simply cannot represent geometry that is far outside because we simply don't have enough bits to do that. So typically we use a fixed point integer representation to represent objects, and as you saw with the camera projection, right, we had to make sure that so geometry can fall outside. They can be as infinitely far away from the origin. So we wouldn't be able to represent the geometry. And if we can't represent the geometry, then obviously we cannot render them at all. The even more important part is that we need to maintain the information so once we cut off geometry, the part that is outside of a triangle or of a line, we still need to maintain as much of the information as necessary. So for instance, if you have a linear shading running across a triangle and you're cutting off parts of the triangle, right, you need to recompute the information at the edge where you did cut off the geometry in order that if you then render the geometry that remains, right, without the parts that have been cut off, if you render that, you get exactly the same image as if you had rendered the large object that has not been clipped. That's the one thing. The other thing is that that makes things a lot more complicated, is that if you cut off pieces of the geometry, you actually end up with a different kind of geometry. In the worst case, you can easily think of the case where in a triangle, you have a triangle where all three vertices, where the center of the triangle is on screen, but the three vertices are actually outside of the window or the screen. And so if you then cut off all three vertices, you end up not with a triangle, but actually with a polygon with 6 edges, right? So, and the hardware cannot even render that, right? Because the hardware can only render triangles. So we actually need to cut off vertices such that we actually represent them as individual triangles, together with the information that if we render those resulting triangles, we actually get the right pixels on the screen with the right color and interpolation and things like that. Even more importantly, and that we'll look at separate algorithms for that, if you want to fill the triangle, so we're not talking about lines, but we're really filling the pixels, we need to make sure that whenever we clip parts of the geometry of a triangle, for example, that the results actually stays a closed polygon, right? Because otherwise we don't even know which pixels are inside and which pixels are outside. So, right, if you take a triangle, just the lines of a triangle, and you cut off the 3 vertices, you end up with 3 line segments, but they're not closed, right? So we actually have to reconstruct the edges where we did do the cutting, such that if we add them to the original, to the pieces of the edges of the original triangles, we actually end up with a closed polygon where we then can essentially use the standard filling and rasterization algorithms with that. So these are all different aspects of clipping, and they're really important. And there's various uses of clipping. Maybe before we dive into that, mention that. I think I have a slide on that a little bit later. Right, they're being used in for mapping map presentations. Right, if you draw labels on a map, first of all, you need to position them correctly, but often you also need to cut off the pieces that might overlap with those labels. The whole labeling part is relevant. So many applications for clipping, besides just rasterization. So yeah, let's first focus on the clipping of lines. So without interior, just lines. And then in the second part, we'll talk about polygons. So where we talk about the interior and we need to keep those polygons closed. There's different algorithms. They seem to be much more complex if you think about them. At first sight, it turns out they're actually not, but we'll get there. So again, in the following, we typically talk about a rectangle that we're clipping to. So that's a typical screen rectangle. But actually clipping can be more general, and we'll talk about some algorithms that can deal with more general geometry to clip against. But in particular, in the context of rasterization, we're typically dealing with rectangular surfaces. Also, you see here that we need to clip, and there's different cases, right? There's trivial cases like the line being completely inside the window, right? In which case we don't need to do anything, and it would be very efficient to identify this case early on, and then simply know that we can essentially don't have to do anything. There's other cases where it's also fairly easy to figure out that we don't have to do anything. So the first case here was a trivial except because it's inside and we don't need to do anything. There's other cases where we can do a trivial reject, right? For instance, this line here on the left, this we can easily figure out that this is completely to the left of the left edge of our window here. And so by definition, it cannot be in the window or on screen. And so again, we can very easily say there's nothing that can happen here, and we don't need to process this. And we can even completely eliminate this line from any further processing because we know it will not be on the screen. There's more complex cases. For instance, the line in the lower right here, right? Yes, it is completely outside, but it's not entirely clear how you figure that out, right? Because if you just move that line here just a slightly little bit, then actually parts of it will be in the window, even though the beginning and the end point are still outside. And so it's not entirely clear how you figure out that this line, it's not easy to trivially reject that. Of course, you have cases where just one end of the line is inside, the other is outside. So in this case, we need to just figure out the point where the line leaves the screen. And we have those cases where it's actually both the beginning and the end of the line will need to be cut off. And we need to figure out the new part where our clipped line starts. So PB is the beginning and the end point, PE is the end point. And we have to, from the original PB and PE, the two original points, we have to define the new clipped beginning and end point that represent the remaining part of the line that actually is on the screen. That's the focus of clipping. So obviously there's a very brute force method to do that. You simply, right, so first of all, if both the beginning and the end point are inside, right, we know because a line is a convex object and the geometry we're clipping against is convex, and if both the endpoints are in, then we know all the intermediate points are in as well. And so we can accept the whole line. We don't need to do anything. So in any other case, in the brute force method, we would have to compute if there are any intersections between the line, so the line defined by the point PB and PE here, and one of the edges. And then we have to do that for every of the four edges in this case. And while we have to compute the intersection point, right? And that intersection point is defined as the point that we get by, right? This is the parametric form of the line equation. So it's the beginning point here, plus some parameter t that runs between the beginning and the end point here. And as we vary the parameter t of the line here between 0 and 1, we sweep the entire line segment. We do the same thing for the edge. So in this case, we're looking at the left edge here. So it's the beginning point of the edge plus t times the endpoint minus the vector from the beginning point to the endpoint. So we do the same thing. And what we're looking for is where a point is equal. So it's on the line and it's on the edge. And we can solve that equation, right? So it's a linear equation in x and y. So it's actually two equations. We can solve that for t. And but we're not, but we also have to check whether the intersection actually is on that line segment and on the edge and not outside of the points of the segment between the beginning and the end point. So we have to check that the two t values here are between 0 and 1, right? And only then do we have a real intersection that we care about. And if we do, then again, we still have to figure out, we know an intersection point, but we still need to figure out if the beginning point is inside or the end point is inside or is on the other side of the edge. So for each edge, we can define each edge essentially defines a half space, right? One half space is in, and the other half space, one half space is out. So for this edge here, right, the left of this edge is the outside, and the right is inside, at least partially inside the triangle. In the screen here. And so we can figure out which of the sides relative to the intersection point we still need to maintain, and then we either replace the beginning or the end point by the intersection point, right? And we have a remaining segment, and then we keep clipping against the other edges here, and eventually we'll find the other. Right, when we test again the right edge, in this case here, we would find the other new exit point in this case, and be able to replace the endpoint by that one. But the thing that's bad about this is that we do a lot of computations, and we are clipping against a lot of edges, where in this case we do a lot of work to find out that, for instance, for the edge, we don't need to do anything. So it's certainly not a very efficient algorithms. Also, we're not taking advantage of the fact that in some cases we can trivially reject a line. That is hard with this approach. So a very basic and important algorithm for handling this more efficiently is the Cohen-Sutherland algorithms, developed in 1974, of course. And it's a kind of divide and conquer approach. By the way, it's funny because like almost all of the clipping algorithms, I think all I'm covering here in this lecture, are actually developed by a pair of authors. And so in this case, it's Cohen and Sutherland, and you'll see that all the others have two authors as well. Just a nice side effect. So here, Cohen and Sutherland realized that, right, it's important to know, to encode the, what they call outcodes of a point or of a vertex. And it's a bit encoding, these outcodes are a bit encoding that for each of the edges of a rectangle in this case, so it's limited to rectangular viewings, screens, clipping geometry. So it encodes for each of the edges whether the vertex is out with respect to that edge or not. Right, so the bit order here is the first bit is whether it's outside with respect to the top edge, the second bit with respect to the bottom edge, the right and the left edge, right? So so this area here is 0, 0, 0, 1 because it's only outside with respect to the left edge, while here on top of that it's also outside with respect to the top edge. And so with these bit codes, and they're easy to, these bit codes are very easy to compute, right? Because they're simply a comparison of the x coordinate of a vertex with respect to the x coordinate of, let's say, the left edge or the right edge. So it's a simple comparison operation. And specifically, if we're operating in integers, it's very, very trivial to compute those bit codes. So the trivial cases can now be identified very easily. So the trivial except code, you can simply find out by looking at doing a bitwise OR of the outcodes of the beginning and the end point, right? Um, because if the OR between the bits are 0, um, that means, so if the OR between the two bits has no bits set, then that means neither the beginning nor the end point was outside with respect to any of the edges, right? And that means it has been inside. Both points, beginning and end point, are inside, and so we don't need to clip, right? We know everything is inside the screen. The next case is the trivial reject case. And here we can only trivial reject if both points are outside with respect to one of the edges, right? And so this we can compute by doing an AND operation between the beginning and the outputs of the end, beginning and end point. And if any of those bits are set, that means both points are outside with respect to the same edge, right? And by definition, that means any point in between is also outside with respect to that edge. And so we don't need to look at that edge at all, that line at all, because we know it is completely outside, and we completely skip that. We can directly go to the next primitive. We can completely forget that. Then the final part is the bitcodes can also be used to identify against which of the edges we need to clip, right? Because if you look at the XOR from the both of those outcodes, right, an XOR, a bitwise XOR between those two values essentially tells you the edge with respect to that one point is outside and the other point is inside. Let's say choose the left edge, right? Then one point is on the left and one point is on the right of that edge. And obviously that means we need to clip, right? There's somewhere that line crosses that edge. It doesn't mean that it crosses that edge, right, within the window, right? It could cross the edge somewhere outside, but we at least know there is a potential intersection with respect to this edge. And so we can limit our computations to only those edges where the XOR of the outcodes has a 1. And so the clipping is now fairly trivial. So you first of all, you compute the outcodes of the first and second point, and then you go through all the edges. We start with one of the edges. First of all, you check whether right, you can trivially reject the thing, then you simply return. Or if we can trivially accept this, then we return and we just give back the beginning, the end point. And then we look at the XOR code with respect to the current edge. And if there is still any intersection with respect, we check whether the current edge has the bit for the current edge is set, and then we simply we can now check which of the 2 points is outside, right? One of the points has to have that bit set and the other not, otherwise the XOR wouldn't trigger. And then we can figure out which of the points we need to replace by the point that is the intersection, by the intersection point. And we maintain the other point. And these are just the 2 cases that can happen. And then, yeah, the critical point is when we replace a point by an intersection point, we also need to compute the outcode of that intersection point, right? Because we will keep looking for, yeah, we don't have an outcode for that new endpoint of the line. So we have to recompute that. And so we keep doing this until, right, either we can trivially reject or trivially accept that, or when the XOR says there is nothing, there is no more edge that we need to clip against them. And that's, it's pseudocode, so it's you can optimize this some more, but it's fairly easy to explain. And then how do we do that intersection computation? Here's an example. Right? It's essentially doing exactly what I showed you on the previous slide. It computes the intersection point. In this case, we know with respect to which edge we're doing this. It's essentially, we can reduce that to a linear, to a 1D computation in this case, and so it's easy to do that. So another way, a little bit more general way of doing this is the Cyrus-Beck algorithm from 1978. It's a parametric line clipping algorithm, and it works on convex polygons, so it's more general than the previous one, even though you can generalize the previous one to more general cases as well. And the nice thing about convex polygons, so it's not limited to an axis-aligned rectangle, is if it's the polygon is convex, then any line segment can have at most 2 intersection points with the edge of that polygon. And this approach uses also the edge orientation, and that will actually be something that shows up in various other ways of in some of the other algorithms, and it will show up for rasterization as well. So again, we will use that parameterize the line that we need to clip in this parametric form here, and then we will compute the intersection points with respect to, so we'll compute the parameters Ti here, and we will sort the parameters Ti with respect whether at that Ti the line actually enters the polygon or whether it leaves that polygon. And that is really something that is important. In order to be able to talk about entering and leaving, we need to have a notion of what's outside of an edge. And to that respect, we essentially compute a normal vector on the edge here that in this case here, we decide to have that normal vector point to the outside. You can change that to point to the inside. That's just you need to just change the tests. So it's the same idea. And so there's an for a point Ti, we can compute whether that's an entry point if the dot product with that normal vector and the vector from the beginning to the end point, if that is negative, and if it's positive, then it's an exit point. And so now we can very easily find out that the part of the line that is actually inside of that convex polygon is from the value from all the entry points that have the largest Ti, where Ti is with respect to the line that we're clipping. And the exit point is the smallest Ti for all the exit points, right? And so you can easily see this here in this case in the upper right, beginning and end point. So the intersection of this line segment, right? We're only interested in the line segment that is beginning between the beginning and the end point. But of course, all the parametric form here is for the entire infinite line, right? And so actually the values Ti's that we're computing is for, oops, sorry. Oh, what's happening? So we actually get 3 entering points, right? The one is with respect to this edge, which is somewhere down here. Then we get this entry point here. And we don't get an entry point for this edge, right? Because it's oriented in the wrong way. And we're looking for the Ti with the largest value T. So we're not looking for this entry point here because right? We're only inside if we're inside with respect to all the edges, right? Since we don't get an inside for this edge here, we're always inside. So we're looking for the entry point with the largest t value. And of course, we're outside as soon as we're outside with respect to any of the edges where we're leaving the geometry. So that's why we're looking for this for the exit point with the smallest t value. And so this is this one here. And you can easily now deal with this case here where there is no intersection of the line with within the clipping polygon here. And that is the case when you leave the geometry. So when the t value with the smallest exit value, if that's smaller than before the entry point with the smallest t value. So you're leaving the geometry before you're actually entering it. And so obviously there is no overlap. And we can completely and trivially reject this case. Of course, we've already done quite a bit of work till this point. So here we cannot have these trivially accept things. We have to do all of those computations. So it's a little bit more expensive, but we can deal with arbitrary convex polygon, clipping against arbitrary convex polygons here. Now, the intersection computations, in this case, you can also simplify this. So we're not in the case where we can simply reduce it to a 1D problem because, right, it's either only in X or only in Y. But here we can actually reduce it to 1D, but we need to do it differently. And here the point is that we're essentially projecting everything relative to the normal vector, right? So, right, the implicit representation of the points on an edge here is if the point P is on the edge, if the difference from P to any point on the edge, right, the dot product with the normal vector is 0. So, right, then this vector on the edge is orthogonal to the normal vector. Then you're on the edge actually. If that point P here is not on the edge, then obviously that has a contribution. That vector here has a component in the direction of the normal vector, and so that dot product is not 0. And so in that sense, you can simplify this computation. So essentially, you're projecting everything in the direction of the normal vector. If you then simplify, then this parameter ti can simply be computed by two 2D difference vectors here, and then the difference between two vectors here, and the dot product with the normal vector, and then the ratio between the two. And again, you have to test whether, yeah, you don't, in this case, you don't have to test whether these TIs are between 0 and 1, because that all of that is being taken care of with the min-max test that you're doing inside here. If you're actually if they are not between 0 and 1, then this case here where the T out is before the T in actually would trigger. You can easily prove that. Another approach to clipping is from Liang and Barsky in 1984. And essentially they are, it's a specialization for axis-aligned, from the Cyrus-Beck algorithms for axis-aligned rectangles. And it introduced the notion of the so-called window edge coordinates. It's just an abstraction of something we just looked at. And the point here is simply that if you have an edge, again, you have this implicit representation here, point P minus some point on that edge times a normal vector, dot product with a normal vector, that actually defines a linear function that is 0 on the edge. And as you go away from the edge, right? It goes positive in one way and negative. So it's essentially a distance function from the edge. And that works for any edges here. And now if of course, if these window edge functions here, this window edge coordinates, if you then specialize them for edges that are horizontal or vertical, then it's clear that they simplify to 1D problems. But you can essentially compute them here as, you can write them as these window edge coordinates of the point, of the beginning point here with respect to some edge t here, so the top in this case that we're looking at here, divided by the window edge coordinate of the with respect to the top edge minus the window edge coordinate of the beginning point minus the window edge coordinate with respect to the end point. So it's essentially, you can say this is the relative location of the point PB here relative to the to the entire edge here. And that gives you the position of the intersection point. And of course, in this case, this simplifies to what we would have done in the previous case. But the point that I'm making here is that these window edge coordinates, this distance coordinates from the edge, are an important point. It will come back to that later. Specifically also for rasterization, because the only thing that really matters here is the sign of that distance function, right? And that's similar to, essentially the sign is what we use for the outcodes in the very first algorithms we looked at in the Cohen-Sutherland algorithms. And the normalization here, for example, is completely unimportant, right? If your dot product, if your normal vector is twice as long, or you scale that by any value, that doesn't matter, right? It's still a distance function, and since you only care about the sign, everything's still fine. Of course, you can't multiply with a negative value because that then changes the orientation and things are different. So if we now look at line clipping algorithms, so there was the Cohen-Sutherland algorithm, Cyrus-Beck, which then generalized this to convex polygons, and Liang-Baski, who introduced that notion of the window edge coordinates. And those algorithms all readily extend to 3D, right? In the Cohen-Sutherland case, you can simply add two more bits for the near and the far plane, and things are fine as long as you're clipping against an axis-aligned rectangle, which you can do after you divide it, or after you've done your perspective projection, you divide it by W, right? You can easily do that, and then you clip against the -0 to 1 value of the normalized device coordinates. So you can do your clipping with respect to the near and far plane there. With Cyrus-Beck, right, there's, so here's a little bit the discussion of what are the pros and cons. So the pros from the Cohen-Sutherland algorithms is, this is most effective if the majority of the lines can be trivially accepted or rejected. And actually that turns out, and we'll come back to that in a little bit, there's an optimization in the rasterization procedure that you can take advantage of here. And it's negative because you might need to reclip the line multiple times, right? Because you clip it with respect to one edge first, and then you clip with respect to the other edge. So you do these clipping operations multiple times, and you're doing these testing for the 3D point coordinates multiple times. Cyrus-Beck, and to some degree Liang-Baski, has a different trade-off when you have to clip many lines, right? Because you do the test only in 1D. And the negative part is that you always need to test against all the edges. And so that's a little bit, for Liang-Baski, you can simplify that, but it's more it's a little bit of a trade-off. So this was for individual lines, okay? And now we're coming to polygons. Now with polygons, again, I mentioned that in the very beginning already, with polygons, we have the issue that we need to fill the inside of the polygon. And if you're now cutting off parts of the polygon, like in this middle case here, for example, you cannot just, let's say, connect the clipped point on the one side with a clipped point on the other side, because that would not define the correct area that still is inside the screen here. So if we clip that triangle against this screen here, then of course I need to fill the entire green part, right? This is simple here in the left case, right? Because it's all only with respect to one edge. But on the right-hand side, you see that things can get much more complex. And you might actually have to fill, if for complex polygons, you might actually have to fill disjoint parts, right? And there's many applications for that, right? The one is just filling with a constant color, but there's also hatching or shading computations where you need to identify all the pixels that are within the polygon, but not clipped by the window. So in general, this seems like a much more complex problem, but it actually turns out it's not. And here is the clipping algorithms that you can apply. And again, it's two authors by Sutherland and Hodgman in 1974. And they came up with an extremely clever idea. The idea here is that you clip against the entire polygon against a single edge first. And if you clip against only a single edge, then things become actually very, very easy, right? Because all you do, for instance, if you only clip against the top edge and you have this complex polygon here, what you do is you simply cut off the part that is outside with respect to the top edge. And that's easy because you can simply, because you're only clipping against one line, you can simply, whenever you go outside, right, you connect, you remember the part where you went outside, and you connect it to the point where you go back in, right? And then once you've done that, then you clip against one of the other edges, like the bottom edge here, and you do exactly the same thing. And then you do this for the other edges as well. And what you end up with is a polygon that is closed, right? Because you always, right, as soon as you went outside, you waited until you eventually come back, where you must come back because you eventually need to connect back to the first point, right? So it's guaranteed that you come back in, and you simply connect the point where you leave the screen and connect it back to the point where you re-enter the screen. So it's really trivial. And because you're connecting them, you also have the guarantee that the polygon after the clipping against one of the edges is still closed, right? Because by definition it is. That's how you construct it. And even better, you can make this algorithm extremely efficient by only looking at the last point and the current point, right? So it's a purely incremental operation. So you remember the state of the previous point, right? So if the previous point was inside, and you have to deal with 4 cases, right? Essentially, whether those cases are whether the previous or the current point are inside or outside. There's 4 possibilities. So the first case is the previous point is inside and the current point is inside. And in this case, you output the current point, right? Whatever you did with the previous point, and you output the current point pi here. The second case is the previous point was inside, but the current point is outside. In this case, you compute the intersection point P here, and you output that point. So you remember the point where you left with respect to the current edge. The third case is the last point was outside, and the current point is also outside, in which case you do nothing because that line segment is obviously needs to be clipped and is completely outside. And so we don't care about this. And then the fourth case is when you go back in, where the previous point was outside and the current point is inside. With respect to that edge. And again, this computation is easy. We just, right, that's what we just talked about. And in this case, you output 2 points, namely the point where you re-entered the polygon and the current point. Right? And this is something that can extremely be implemented in hardware extremely efficiently, right? Because you just need to remember the state of the previous point. And for the current point, you need to compute whether it's inside or outside. And only if that is different, right, the inside-outside decision is different between the 2 points, then you need to compute the intersection point, and that we know how to do that. And so you can now build hardware that even doesn't need to store the entire polygon, right? All you need to do is define 4 pieces of hardware where each one does what we just looked at, looks at these 2 cases. And the first piece of hardware clips against the top, the second against the bottom, and so on. And you simply feed it the number in order, the vertices of the polygon. And what you end up with is the clipped polygon that comes out, right? And each piece of hardware only needs to look at 2 points at every point in time. Now, there are some problems, let's put them in quotes maybe. So if you use this Sutherland-Hodgman algorithm, and I showed you that maybe the result of that is what looks like disconnected parts that remain, they are actually not disconnected with this algorithm, because if you clip this polygon against this rectangle here, what you will create, let's start with this point here. So we enter the polygon, so we record this point, we're inside, we stay inside, then we record this point, we're now outside, this is outside, we don't do anything, and so on. Eventually, we come back in. And so what we get really is this polygon that here we enter, we go this edge, then we go back here, then we go all the way back down here, and then here, and then through that red line. So this red line here, this line segment that is shown here in red, this is actually a degenerate part of that polygon, right? Because we go down here and we go up this piece here. And if you rasterize this polygon with whatever kind of rasterization algorithms, essentially this, you would figure out that you don't need to do anything here, right? Because these 2 edges overlap and you wouldn't rasterize. There's no pixel who can be inside of this infinitely thin part of the polygon. And that's easy to handle in a rasterization approach, or you can do some post-processing that actually splits the polygon into disconnected pieces and eliminates the red part. We don't cover this here, but it's not trivial, but it can be done. For rasterization, again, it is trivial because you can design the rasterization algorithm such that it would never render these infinitely thin lines at all. There's a number of other clipping algorithms that I don't have time to actually go into. There is the Weiler-Atherton algorithm from 1977 that allows to even clip concave polygons that might contain holes, and you can clip them against each other. There is the Vati algorithm from 1992, where these polygons might actually overlap themselves. So there's you see this here on the right? So the polygon overlaps itself. And of course, in this case, you have to define what is inside and what is outside. And there's the winding rule that you typically use for that, right? So for the green parts, the polygon wraps, right? If you follow the polygon, it wraps around a point in the green area once. But if you look at this bluish area here in the interior, you actually see that the polygon wraps around these points twice. And we already looked at, when we talked about intersection computation, we looked at this winding number. No, sorry, we were looking at this when we talked about rasterization. So that's coming up. The final algorithm that I'm aware of, there might be others, is by Greiner, Günter Greiner, and Kai Hormann. Greiner was a professor at Erlangen University, where I did my PhD while I was still there. And Kai Hormann is now a professor in Switzerland. He was a PhD student at the time, and they figured out that there's even a simpler and faster way to handle with these general polygons than was presented with Vati. And it also supports Boolean operation. And the idea is really pretty trivial. I don't have time to go into details here, but simply you can split one polygon into two classes of segments, where you can simply switch. So as you walk around one polygon, right? Let's say we start here. We can compute the parts that are outside with respect to the other polygons. So here we're outside, we're entering here. So now from here on, everything's inside until we hit the polygon again, at which point we switch to being outside again until we enter again here. And so essentially you can divide each polygon in the parts that are inside with respect to the other polygon and the part that's outside with respect to the other polygon. And once you've done that, you can now easily do funny Boolean operations with them, with this, where, for instance, you can look for the polygon, right, for the polygon of A that is in B, or for B that is in A. And if you take the union of these, right, then you get actually the computation of the part of the intersection of these two polygons. And again, you get, if you switch, right, here where I'm inside, when you go outside, you switch to the segment from the other polygon and to this part here, in which case you now, right, here you have to switch to the inside of the other one again, and so on. So you do create a closed polygon again, and so, but you can do even more complex operations. So this idea here is, this odd winding number rule is being used here because each intersection of one polygon with respect to the other polygon changes that winding number by plus or minus one, depending on whether you're entering or leaving. And so you can simply walk along one of the polygons with respect to the other one. You have these alternating winding number rules, and combined of that, if you then combine these two things, then you can do all of these operations that I just mentioned. Very nice and very elegant algorithms, actually fairly trivial to do that. It's very nice. So this was all in 2D. And now we can also think about, and briefly mentioned that already, we can also do the clipping against 3D. This we don't have to do. We're doing this to avoid unnecessary computations with rasterization, and most importantly, because the rasterization itself, actually, as I mentioned before, typically happens in fixed point, and so by doing this operation, we avoid any overflow. Remember that we divide by W in the perspective transformation, right? Because we do this in homogeneous coordinates. And so that's, again, what I mentioned last time. We need to cut off everything that's getting too close to zero, because otherwise we would divide by something that is zero or close to zero. And again, that would be either we get division by zero error, which is not good. Or we divide by a very small number where the result would be very large numbers, which we likely couldn't represent with a fixed point anyway. So by cutting off the relevant pieces also in the z direction, we avoid all of that. Yes, and so we can do that clipping either after the perspective division, so by dividing, before we divide by W, by simply clipping, sorry, after we've done that perspective division. Now we're back in normal 3D coordinates, and then we clip simply against, right, X and Y. We define this -1 to 1, and in Z between -1 and 0. And so we can use any of the algorithms we just looked at. But it turns out you can actually do the clipping also before the perspective division by W. You can actually do the clipping in homogeneous coordinates. And that is quite funny because it also, you can do this with respect to window edge coordinates, which are just defined slightly differently. So again, we now are clipping against this perspective viewing frustum, right? In the canonical view frustum, I should say, where the sides of the view frustum are at 45 degrees with respect to the z-axis. And so in this case, the left, for instance, is defined by, of the left side of the viewing frustum is defined by the slope of x with respect to w, so x divided by w, that must, right, that's the, if we do that division, right, that must be larger than -1, so then we're inside. But we can actually, we can bring the w here to the other side and simply define window edge coordinates for that edge here as w plus x in this case. So we multiply by w, bring it to the other side. So w plus x must be larger than 0. And we can define this w plus x as the window edge coordinates for the left-hand side. And we could do the same for the top and so on. We can also do this for the back and front near and far planes. So with these computations, we can do exactly the same algorithms that use window edge coordinates as we've discussed them before, except that our window edge coordinates are defined slightly differently now. But the same approach still holds, right? If you just replace the window edge coordinates here with the function as we defined it up here, you do exactly the same algorithms. And since we're not doing this division here, we can actually do it in homogeneous coordinates, and we can eliminate geometry and not do the w division by w. Again, divisions are expensive in hardware. We can eliminate the geometry even before we do the division by w. However, there is a problem with homogeneous coordinates because under certain circumstances, and that specifically happens if you're dealing with non-uniform rational B-splines, for example, where the W is used actually slightly differently, but you're using the same framework for homogeneous coordinates. And in this case, it can happen that the W actually becomes negative. And that's a funny thing, right? So let's look at a line between the point here, a beginning point here, and an end point here, where the coordinate system is slightly differently. So it's very hard to draw 4-dimensional coordinates. So here we're doing a 2D slice. So in the horizontal direction, we have the X direction. And in the vertical, it's not Y, but it's actually W, right? So we now have a line that goes from a point PB with a negative X value here to an endpoint that has the same negative x value, but has negative w, right? So here, let's say it's w plus 1, here's w minus 1. And so if you draw that line segment now in this 2D slice of the 4-dimensional space, yeah, let's assume, I don't know, y and z are 0. If you draw this line now here, that actually goes here, right? It goes down here. However, now this is in homogeneous coordinates in this 4D projective space, right? But remember that to actually draw the line, we are converting back to 3D by dividing by W. And now, if you think about this, now as you go down from the beginning point, let's follow this line. As we go down here, right, we're dividing by W. What does that mean? Well, we're projecting onto the line where W is equal to 1. So from the origin, we're projecting those points onto the line here, in this case, where W is equal to 1. Right? So essentially, as we, in homogeneous coordinates, go down here, in 3D coordinates, we're projecting this onto this line here. And what we need to do, so essentially this line goes here out to minus x infinity. Sorry. So this line goes here out to minus infinity. Right, as we go down here, it projects further and further out. For W0, it would project to minus infinity. And then as we go further down, right, we're dividing by minus W. So the points actually come back in from plus infinity in x, right, all the way until the end point here, right? So all the points down here project, those points here project to this light blue segment over here. And so what we need to come up with now is a clipping algorithms that can deal with this. And these window edge coordinates that we just defined here on the previous slide, let me just go back, right? They deal with this, right? Because, right, they don't divide by W, so they simply, they do clip against exactly this 45-degree cone here. But what we need to do is actually we need to clip twice, right? Because we, at one point, we need to clip here this point from the beginning to minus infinity. That's the first part of this line. So you clip from the beginning point to the intersection point, where you kind of leave the frustum. And then we need to multiply, we need to change the sign of the W coordinate, which essentially, if you do that, you're mirroring those points at the origin. So the PB becomes minus PB here. So we're changing, we're multiplying this whole thing with -1. So our beginning point moves down here and the end point moves up there. And now we're clipping that line, which means we're clipping this line here, against this segment from the end point towards the intersection point, which gets projected up here. So we get this other bluish segment here on the right. Right. So even you can deal even with these degenerate cases where W goes through 0 and you would project until infinity. We can even deal with those cases in the clipping algorithms. And now finally, let me just take drink a bit of tea. Yeah, so actually, let's look at some optimizations. As you saw, clipping is something that is not really as nice as you would like it to be for hardware, right? The first issue is that you can clip a triangle and end up with something that is a hexagon. So a 6-sided polygon. And that's an issue, right? Because you can't directly render that. And so you have to do You have to do special cases for that. The other thing is you don't know, right? For any triangle, you might end up with nothing because the entire triangle gets clipped away. You can end up with a 4-vertex polygon, 5 or even 6-sided polygon. So it's that all of those things, this flexibility that can happen during clipping, makes things complex, and also, right, with the clipping algorithms, you figure they were not trivial to implement. And so essentially the lessons here is ideally we would like to get away with not doing any clipping at all, or at least doing this as few times as possible, right? So now, first of all, now you think, well, but I cannot avoid that, right? Because there can always be geometry, right? If I move my camera around in a 3D world, it can easily, right? You can easily construct cases where geometry goes from something that's inside to something that's far outside. So it's very, so you cannot really, from that point of view, you cannot avoid generating cases where you have to clip. However, there is a trick you can play by taking into account that most applications are actually intelligent. And if they render something, they don't simply render everything, but they trend to only render the parts that are likely to end up in the viewport, right? In the window that actually gets rendered. Most applications, I should say, are trying to identify geometry that will not end up near the window at all. And if you take that into account, then you can do a trick. So, but before we go there, so what applications are actually doing is, right, they look at their view frustum of their current camera, and then they have the different objects that they're rendering, and they for instance take the bounding box of that object, and they can be done fairly trivially. That's essentially a sort of culling algorithm. If the bounding box of that object is right to one of the sides of the viewing frustum, then you know it cannot be inside, and you can completely eliminate the entire object, right? So that's not a clipping operation, that's called culling, because you're culling an entire object without looking at the individual lines or triangles inside the object. It's pretty similar to the acceleration structures we're using in ray tracing, right? Where you have a bounding volume of an entire subtree of your scene, and if your ray doesn't intersect with that, you don't have to look any further. This is the same thing here for rasterization, right? If you want to render an object, you look at the bounding box, and if that bounding box is completely outside of the view frustum, you don't care, and you're not actually sending that geometry to the GPU at all. Now the trick, so for applications that do that, there is a trick. And sorry, but before we go there, one more thing. So in some cases, the application, however, cannot identify that it is outside. So there are cases where the entire geometry is only a tiny bit outside, but the bounding box overlaps with the viewing frustum, or the object is actually partially inside and partially outside of the viewing frustum. In those cases, the application typically submits the entire objects for being rendered. So it doesn't actually do any clipping operation, but it just renders the entire object. However, now here's the trick. Remember that the biggest issue that we're dealing with is that we're dealing with fixed point. The rasterization happens in fixed point, and so at some point we cannot represent the geometry. The trick now is that, well, if you need so many bits for the window itself, right, why not add a couple of more bits so we can represent some area that is outside of the window, or the viewport, as I call it here on the screen. So in this one, I actually want to clip the viewport, the part on the window that actually I want to render, right, is here in this dashed line. It's this blue shaded area. So what I do, I add a few more bits to be able to represent more geometry outside of this. And now I'm not clipping against the viewport, but I'm actually clipping against the area that can be represented, which is now much larger, right? And so what happens if you do that, here, these triangles should actually represent entire objects. So some of these objects here, the application can figure out that it will not actually be able to be inside the viewport, and it will not submit that geometry, and I don't need to do anything. However, sometimes here, as for this object here, that is partially inside the viewport, there is a good likelihood, right, that this object will be close to the viewport, but still be within the clipping region, right? Which means I can represent the object in fixed point, which means I don't have to do clipping in this case, right? And so because the object is completely inside the clipping region, so I can trivially accept everything in that object. Right? The application would submit it. I would look at whether I clip that, but I would figure out I don't need to do any clipping. Everything gets trivially accepted here. And now the trick is the rasterization. As long as I can represent it, in the rasterization algorithms, I can now take care of only rendering the piece of that geometry that's actually inside the viewport. We'll look at that next. So essentially the trick is, by enlarging the clipping region, making this larger as the actual viewpoint that you're rendering, you vastly increase the chance that you never have to clip anything, because the application does not submit things that tries to not submit things that are far outside of the viewport, right? And so most of the things that do get submitted, the vast majority typically of the things that do get submitted, would fall completely inside the clip region, and I wouldn't have to do clipping because I trivially accept that. So there's a little bit of penalty still, because you still have to do the setup, and you have to do the preparation to actually rasterize things. And then, right, if a triangle is fully inside the clipping region, I would try to rasterize it. So even the triangle here on the left, I would try to rasterize it. Or would start to rasterize and only then figure out, well, actually, I don't have to. But that can be fairly efficiently dealt with in the rasterization approach, and we'll talk about this once we get there, which is actually the following lecture. And that brings me to the end of the clipping part. We still have some time, and so I can start talking about rasterization. But before I go there, let's see if there's any questions that you might have with respect to clipping. No questions? So in this case, let me switch to rasterization, and we're a little bit early, but that's fine. So we can start with that. Okay, so remember where we are. We have a 3D scene. We have been able to project that onto a 2D screen. We've been able to cut away through clipping all the pieces that were outside of what I can represent in, for instance, fixed point. And now I have the final part now is switching on all the pixels that are needed for actually drawing that object onto a raster display. So that is what we need to do. So given some 2D geometry, so we've done everything, or sometimes it's 2.5D because I keep the Z value around. We'll get back to that. But mainly we think about objects now in 2D. And there could be points, there could be lines, circles, triangles, and polygons, right? And we'll look at some of these elements. And we, right, so we now need to find out which of the pixels of the raster display are being covered by that object. And that process is often called rasterization today. Previously, what also called scan conversion, because some of the algorithms actually work on a scan line basis, and so it's right, they operate on one scan line at a time and then go to the next scan line. That's where the term scan conversion comes from. Now, the rasterization has also different meanings. I forgot to mention the second part here. So anti-aliasing, so in the following, we will only consider pixels that are either fully covered or not. So we only think about doing a single sample, which we typically do in the center of the pixel. Now, if you want to do anti-aliasing, what you typically do is actually have multiple samples within a pixel, which then is called supersampling or multisampling. So essentially figuring out which parts of the pixel are covered by that primitive. We're not dealing with this here, but it's not difficult to generalize what we're talking about here for that anti-aliasing part. Eventually, you have to resolve that to a single color and alpha value. We'll talk about that a little bit later. So for this rasterization process, there's now two ways to look at strike, two perspectives. The one is how does the actual rasterization operation work? Like what is implemented on the GPU, right? How does the GPU figure out which pixels to draw and which not? That is what we'll look at in this lecture now. But there's also, so that's essentially the point of view of a graphics hardware implementer, or you can also implement it in software, of course. But there's also the point to look at from an application point of view, which is like, how do you drive a rasterization engine? And so how do you actually submit the geometry to the GPU? Whatever then the GPU does, you don't care about. You just look at the instruction set, essentially, of a rasterization engine. And that is something we will look at right after we finish this lecture, which we start today, but we'll continue on Monday. Rasterization, of course, has many other usages. So there's 2D rasterization. So for instance, in a printer for PostScript or PDF, right, you need to convert, which are high-level descriptions of polygons and colors and right, color gradings, linear rams of colors and fonts that need to be rasterized, all of that stuff. There's also simple vector graphics, which is being used for describing vector graphics for graphical user interfaces, for example. So as PDF is, of course, used on the screen, but in the printer, SVG is mostly used on the screen, but can be converted quite easily to PDF as well. But you also need 3D rasterization sometimes. So for instance, if you want to do a grid, if you want to compute the grid structure for ray tracing, which you need to figure out which of your triangles are being covered by which cells in your 3D grid. And that is a rasterization operation, right? You need to insert that triangle data structure into each of the grid cells that are covered by that triangle, 3D grid cells that are covered by that triangle. It's actually, it's actually what's called a conservative rasterization approach. So it's a little bit a slight variant of what we're talking about in the following here. I'll come back to that. Also, volume operations are often accelerated by creating such acceleration structures, so doing CSG operations, collision detections, spatial indices I already mentioned. So there's many applications where you need to figure out for a 3D grid which objects are where, which need to be inserted where. There's many applications. So that's the one thing. So it's important. Even right, if today we typically don't have to implement it for OpenGL for rasterizing onto the screen, because that's what the GPU does for us. For many of the other applications that I just talked about, they're still, in many cases, you still need to implement them yourself, and that's so they're relevant. So for the following discussions, we make a number of simplifications. So we are not considering pixels as areas, but we're considering pixels as samples. So they're infinitely 0D entities. So they're points on an integer grid. So, right, every pixel is one integer, x and y, described by an integer coordinate in x and y. In OpenGL, it's actually that the sample is at the lower, or the origin of the pixel is in the lower left-hand corner of, that's where the integer coordinate is. In X11 and the book by Foley van Dam, they consider the integer coordinates to be in the center of the pixels. So you need to be a little bit careful there. So if you do anything with OpenGL, if you want your integer coordinates to really be in the center of the pixel, you need to kind of shift everything by half a pixel, which is important to consider. You see this in some OpenGL applications. Also, we're just mostly only thinking about simple raster operations. So either we set a pixel to some color value or we don't. So it's a binary decision. We will briefly talk about some more complex operations, compositing and anti-aliasing, where you actually need to do more. That's a whole story in itself. We only kind of talk about this very briefly. Also, we are assuming that our endpoints are snapped to those integer locations. So we're not considering like floating point coordinates for rasterization, but we're kind of rounding them to the nearest integer locations. Even if you do anti-aliasing, where you have samples within a pixel, they are simply on a finer grid, and so you can still do that by just essentially zooming a higher resolution screen. That just makes all of the computations more consistent and simple, because we don't have to, we're only dealing with fixed point arithmetic here. Finally, we're limiting our lines to have a gradient or a slope of an absolute value smaller than 1. Actually, in most cases, we'll assume that the slope itself is between 0 and 1. So essentially, these are lines that are mostly horizontal, right? At most at minus 45 to 45 degrees slope, or 0 to 45 in many cases. And so essentially that means they have more points, so more pixels in the x direction than they cover in the y direction. And so you can think of them as using the x coordinate as a driving axis, and then figuring out where we need to, for each x, we need to figure out where is the y coordinate that we need to render. And that's not a major limitation here, because we can simply generalize this. So if we want to mostly vertical lines, for example, then we just switch x and y, do the whole thing, and then before we actually rasterize things, we're switching back, and we just set the pixels as needed. In software, that's a little bit of if-thens. in hardware, that's a single bit that you need to switch two lines. So it's trivial there. Also, we will assume that the line width is 1 pixel. And that means for the mostly horizontal lines, right, there's a single pixel we're setting for each x coordinate, or 1 pixel for mostly vertical lines. There's y is the driving axis. There's 1 x pixel that we're setting. Now we'll at the end we'll talk also about thick lines as generalizations, but we'll get there. So first of all, we look at the rasterization of lines. And so we specify those lines with getting a beginning and an endpoint, so x and y of the beginning, x, y of the endpoint. And we also can compute the difference between the two, so dx and dy, which is simply xe minus xb, and so on. And also we will look at the line in its functional form. So y given as a function, so mx plus b, so it's a linear function here. And again, these coordinates here, x and y, are integer coordinates, which means that the slope m here, dy divided by dx, is a rational number, right, given by this ratio dx by dy. And so the goal is that for each column, again, we're using x as a driving axis here, we want to find the pixel that is closest to the line, right? And then we set that pixel. And now the brute force algorithm is really trivial, right? So we iterate from the x coordinate of the beginning start point to the x coordinate of the end point. Then for each xi here, we compute the y coordinate with this linear function here, and then we round that y coordinate to the closest integer, and then we set the pixel given by the current x coordinate and the rounded y coordinate. Now, the drawback of that is that the computation of y here, we have to do this in floating point, right? Because that is a rational number, and it's no longer an integer. And we have to do the round operation, we have to do a multiply, and we have to do an addition, and so on. So that's not nice, right? And it's not suited for hardware implementation. I mean, the good floating point algorithms are as fast as integer now, but they're considerably larger in terms of area, the amount of hardware we need to do that. So that's not good. There is a different way of how we can describe that if we kind of do this incrementally. Yeah, actually, given that we're almost running out of time here, let's leave it at this, and I'll pick this up again on Monday. So we'll simply look at different, more efficient ways of rasterizing lines, and then we'll generalize this to triangles and polygons, and see that we can actually do things very, very efficiently. Yeah, so we used a little bit of our times today for already starting with rasterization. Again, is there any maybe final question that came up that you want to use the time to ask this? Feel free to either use the chat or just ask on the audio channel. Maybe while you think about questions, there was a question last time about the volume rendering part. If you look at the agenda for this course now, we've moved that towards the end, so we'll do the rasterization related lectures, and then depending on how much time we have at the end, we'll talk about volume rendering, where most likely we'll be able to get there. So just to answer that question. I don't see any questions here. Then thank you very much for today. And we'll see each other, well, you will see me, I guess, on Monday, and we'll continue talking about REST resection. Looking forward for that, and see you on Monday then. Bye-bye.